Here we are going to look at how to calculate volumes of solids of revolutions using cylindrical shells. So previously we looked at calculating volumes of all sorts of solids, including solids of revolution, using slices. And if I was to do a shape like this using slices, then I would probably be slicing at different y values. And if I was to slice a particular y value, say this y value here, then I would have a circular washer-shaped slice. So it would look like this. Okay, and the challenge with that is that I would have to find two different radii, which would be two different x values. So at that particular y value, I would have to be able to find the x values from these two different points. And that is often difficult, if not, well, I mean, it's very rarely impossible, but it's a very difficult problem. So this is going to offer us another approach. And it's nice to have a couple of different approaches that you could choose from. So what we're going to do, so in this particular picture, I have a region in the XY plane. So this is the XY plane. And it is, in this case, rotated around the y-axis. Okay, so you can kind of see that this region here corresponds to, let me see if I can do this. There it is here. And then it got rotated around the y-axis, and it creates this solid. Okay, so what we're going to do is we want to integrate with respect to x, since this curve has y defined as a function of x. So we are going to, as we have before, take our interval from a to b, and we're going to divide it up into n equal subintervals. So this process should look familiar to you. And each of the subintervals will have width, which we're going to call delta x. And that is just going to be the length of the whole interval from a to b divided by n. So that's going to be b minus a divided by n. Okay? And what we're going to do here is, in the ith subinterval, again, what we have is, a is going to be labeled as x sub 0, and then there's x sub 1, and x sub 2, and so on, up to b would be x sub n. One before that is x sub n minus 1. And if we pick out some generic subinterval in the middle, the ith subinterval is going to be from x sub I minus 1 to x sub I. Okay, and in that interval, we're going to pick some value, which we're going to call xi star. And we're going to use the value of the function f at that representative x value to determine the height of a little rectangle. And we're going to take that little rectangle and we are going to spin that rectangle around the y-axis and see what sort of solid we get. And the solid we get will be what we call a cylindrical shell. So let me see if I can draw that. So technically, we probably wouldn't see this wall in here, and I'm going to dash that last bit. So think about this as being kind of a cylinder that has a wall that has some thickness. The cylinder does not have a bottom. And so, but it has some thickness to it. And therefore it has a volume. And in order to gather the approximate volume of that cylindrical shell, I will take it and imagine like slicing open this cylinder around like right here. Imagine slicing it open there. And if I slice it open and open it up, I hope you can imagine that what you would get is a very long rectangular slab. It would probably look something like this, and it would have a thickness. It would be, the thickness of it would be delta x. So this width is delta x, right? That's the width of the rectangle or the width of the subinterval. So that there is delta x. The height of this large rectangular slab is going to be f of xi star. And then what would be the length of this rectangle? If you think about where this rectangle came from, that length of the rectangle should be the circumference of the whole cylinder. So circumference is 2 pi times the radius. And the radius, in this case, is going to be the x coordinate. I want to move things down just a tiny bit. So the radius here is xi star. Okay, so I'm going to have the length of that slab when I open up that cylindrical shell is going to be 2 pi times the radius, which is xi star. Now, the volume of this little cylindrical slab, so it's the volume of the ith cylindrical shell, would be length times width times height of this rectangular slab. So this would be 2 pi times xi star times the height is f of xi star times delta x. The total volume can be approximated by a sum of all of these volumes of cylindrical shells. So I equals 1 to n of v sub i's, which is the sum from I equals 1 to n of 2 pi xi stars times f of xi stars times delta x's. As we've seen before in other processes, we get a better approximation by increasing n and taking more subintervals. And so we will define the actual full volume to be the limit of this process as n goes to infinity. And I hope that you recognize this limit at this point. This is a Riemann sum. So this limit is going to be equal to the integral from a to b of the function that we are integrating would be 2 pi x times f of x dx. Okay, so this is how we're going to calculate the volume of the whole solid using cylindrical shells as our object of integration. All right, let's see what this looks like in practice. And I'm going to be very careful to sort of draw pictures of a lot of these pieces in my images here. All right, let's take a look at this one. So we have this region that is defined by the area under the curve y equals 1 over x. For x goes from 1 to 3, we're rotating that region around the y-axis to create this solid. So I'm going to just make a mark that says that we are rotating that around the y-axis like this. And I am going to try to consistently draw one x value. So I'm going to choose an x value, and I'm going to draw the vertical stripe through that x value and show what that looks like in rotation. So when that gets rotated around, I'm going to get this cylinder. And I'm also going to, and I encourage you to do this as well when you are starting this out, I'm going to draw what that cylinder looks like as a rectangular slab. So that is going to be something like this. And I'm going to just add a little bit of thickness so that x value is kind of thought of to be just a single x value, but it comes from thinking about dividing that interval into subintervals that are very, very skinny subintervals. And so this slab is going to have thickness dx. Okay? The height of that slab is going to be the same as the height of the cylinder, which is going to be f of x. And my radius here is going to be just the x value. So again, the length of that big rectangular strip is going to be 2 pi times the radius, which is 2 pi x. Okay, so looking at the volume of these rectangular strips, which come from cylindrical shells, I'm going to be integrating length times height times depth. So 2 pi x times f of x times dx. And my x coordinates, my x values, or my radii of my cylinders are going to range from 1 to 3. So the volume is integral from 1 to 3. Let's pull that 2 pi out since it's a constant. So 2 pi times the integral from 1 to 3 of x times f of x is 1 over x times dx. So this is 2 pi times the integral from 1 to 3 of just dx. You can go ahead and anti-differentiate that, and you can also think about this as being, this is really adding up all of the little dx's for x going from 1 to 3, which is really just the length of this interval. So this is 2 pi times 2, which is 4 pi. Okay, so the volume of this particular solid is 4 pi cubic units. All right, let's try this in another example. So here we have, again, this region here is defined to be the area under the curve of f of x equals 2x minus x squared, ranging from 0 to 2. And we're rotating around the y-axis. So again, I'm going to draw that rotation there. So again, I am going to pick an x value in that interval, and I am going to draw a vertical line and then see what happens when I rotate that vertical line around the y-axis. So that's going to give me a cylinder that looks like this. And if I cut that open and unwrap it, it will give me a rectangular strip that looks like this. And I want to think of that line as having a little bit of thickness. The thickness of that line would be dx. And so that would be the thickness of this slab when I unwrap that cylindrical shell. Okay, so that thickness is dx. The height of this is going to be f of x. And the radius here is going to be my x value. So that means that the length of this rectangle is going to be the same as the circumference of that cylinder, which is 2 pi times the radius, which is 2 pi x. Okay, so the volume here is going to be 2 pi x times f of x dx. Now, in this, I should probably say the volume of the ith piece. I'm not really labeling the indices here, but it's good to note that that's the volume of one piece and not the whole thing. So my whole thing, the volume is going to be, I'm going to be integrating all of these cylindrical shells, which all have volumes of 2 pi x times f of x dx. And my x values are going to range from 0 to 2 in this case. So this is now, I'm going to pull the 2 pi out, integrating from 0 to 2 of x times 2x minus x squared dx, which is 2 pi times, integral from 0 to 2 of 2x squared minus x cubed dx, which is 2 pi. This would be 2/3 times x cubed minus 1/4 times x to the 4th, evaluated from 0 to 4. No, evaluated from 0 to 2, which is going to be 2 pi times, this would be 2 times 8 is 16/3 minus 16/4, and that all simplifies to 8 pi over 3. So my volume in this case of this solid is 8 pi over 3 cubic units. Let's do another one. This setup is, we're rotating a region Q, which is defined as x as a function of y, and we are rotating around the x-axis this time. So we could do this by slices. This one would be not that hard to do by slices, probably. In which case, if we wanted to do this by slices, we would be integrating with respect to x. We would be taking a slice at each individual x value. But let's do this with cylindrical shells, where we're taking a different shell at each individual y value. And so what I want to do here is, again, pick a y value, and we're going to pull up a line across that region, and we're going to see what it looks like to rotate that line around the x-axis. Now in this case, if I open this up as a strip, I'm still going to draw the strip. I'm going to open it up and still draw the strip long ways this way. And I'm going to continue to draw it with a little bit of extra thickness, just to remind ourselves where that formula comes from. Don't use formulas blindly and try to memorize them. That is dangerous. So the thickness of this strip would be dy, right? That's like the thickness of this strip here. And my height is going to be g of y. Now, in this case, my radius here of the cylinder is going to be my y value. And so the circumference around is going to be 2 pi times the y value. So I am going to to calculate the whole volume, I'm going to be integrating 2 pi y times g of y times dy. And my y values in this region are going to range from 0 to 4. Okay, so my g of y is 2 times the square root of y. So this is, I'm going to pull that 2 pi out. And I'm integrating from 0 to 4. Y times g of y is 2 square root of y, and I'm going to write that square root as y to the 1/2. Okay, pull that 2 out, so we have 4 pi. And this is y to the 1/2 times y to the y times y to the 1/2. Integral from 0 to 4, this would be y to the 3/2 power. So 4 pi times, this would be, using the power rule, increase that by 1, so y to the 5/2 power, and divide by that 5/2, which is the same as multiplying by 2/5. Evaluated from 0 to 4. So this is going to be 8 pi over 5 times 4 to the 5/2 minus 0 to the 5/2 power. Looks like 8 pi over 5 times 32, which ends up being 256 pi over 5. So the volume of this thing is 256 pi over 5 cubic units. All right, let's do another one. Okay, here we have a region given as the area under the curve y equals x. And here we're going to rotate it around the line x equals -1. Again, it is very good to think about building all of these parts of the picture. So I'm going to re-emphasize that this is the axis of rotation, the x equals -1 line. And I'm going to pick some x value and draw that vertical strip for the x value, and think of what it looks like to rotate that vertical strip around that line, the axis of rotation. Now when I cut that open and get my rectangular slab, it's going to be very long indeed. It's going to be even longer than this, but I'm just going for basic representation here. Again, I want to try to draw some thickness. You don't have to draw the thickness if you don't want to, but I recommend you do for the first couple that you do for this, just to remind yourself where all of the parts of the formula come from. So this is you want to think about this as being a rectangular slab that has a little bit of thickness that you're calculating the volume of. So the thickness is dx. The height of this function is f of x. And the width of the strip is going to be 2 pi times the radius. What is that radius? The radius here is not just the x value, it is x minus -1, which is x plus 1. Okay, and you can see that in the picture. Here's the x value, and then I'm adding 1 to it. So the circumference of that cylindrical shell, and therefore the length of this rectangular strip, is 2 pi times x plus 1. So my volume is going to be an integral of 2 pi times the radius, which is x plus 1, times f of x times dx. you should be able to see this is going to be the length times the height times the depth of that rectangular slab. Okay, my x values that I'm integrating over are going to go from 1 to 2. Those are the x values that are defining my interval, my region. So this is going to be, I'm going to pull that 2 pi out, integral from 1 to 2, and it's going to be x plus 1 times, in this case, f of x is equal to x dx. So 2 pi times the integral from 1 to 2 of x squared plus x dx, which is 2 pi times 1/3 x cubed plus 1/2 x squared, evaluated from 1 to 2. 2 pi, this would be 8/3 plus 4/2 minus 1/3 and minus 1/2. So this is 2 pi times, let's see, that's 7/3 minus 3 or plus 3/2. I'm going to multiply that 2 through. This is pi times 14/3 plus 3. That is 14/3 plus 9/3 is 23 pi over 3. So the volume for this solid is 23 pi over 3 cubic units. All right, I have 2 more examples here. So here is a region R that is defined as being between 2 curves. And we're going to rotate it around the y-axis. So again, I'm going to just kind of indicate that. And I'm going to pick an x value. There's my x value. And I'm going to take a vertical slice through that region. And I'm going to see what it looks like to rotate that vertical slice around the y-axis. And notice, let's see, let's draw that out. It's going to be a very long, skinny strip. I'm going to draw the extra thickness there too. So that thickness is dx. My radius in this case is going to be my x. So this width is going to be 2 pi times the radius, which is x. And the height here is going to be, the upper curve is given by f of x, and the lower curve is going to be given by g of x. So this height is going to be f of x minus g of x. So now my volume is going to be the integral of 2 pi x times f of x minus g of x times dx. My x values are ranging from 1 to 4. So this is going to be, pull out that 2 pi, integrating from 1 to 4, x times, f of x is x to the 1/2 power, and g of x is 1 over x times dx. So this is going to be 2 pi integral from 1 to 4 of x to the 3/2 power minus 1 dx, distributing that x through. So 2 pi times, this will be x to the 5/2 power, and then divide by 5/2 or multiply by 2/5 minus x, evaluated from 1 to 4. 2/5 times, I'm going to evaluate each one of these pieces from 1 to 4. So this will be 4 to the 5/2 power minus 1 to the 5/2 power minus 4 minus 1. 2 pi. 2/5 times 4 to the 5/2 power is the same as 2 to the 5th power, which is 32 minus 1, and then subtract 3. I'm going to skip ahead on this fraction computation, so this ends up being 94 pi over 5. So the volume of this solid is 94 pi over 5 cubic units. All right, one more bonus one. If you watch the videos on calculating volumes of revolutions with slices, you might have seen me do this one, and it was not fun with slices. It was doable, but it was a lot of work, and it involved integrating with U substitution. And I just want to share that it's a lot easier in this case. So in this case, I have, we're rotating around the axis x equals 4. So I'm going to go and draw that axis. We're going to rotate around that axis. And so that's what it looks like here. It's this sort of lampshade looking thing, a lampshade with some thickness to it. And again, I am going to pick some x value and go and draw a vertical stripe through that x value, or through the region at that x value. And I'm going to take that x value and I'm going to rotate it around the axis of rotation. And I'm going to draw the strip. By the way, when I'm eyeballing these, the circumference is pi times the diameter. Pi is a little over 3, so I'm kind of eyeballing it to be where this length is roughly 3 times as long as that. I don't know how accurate I'm getting, but that's sort of what I'm doing here. I'm going to draw that with a little bit of thickness. So there is the thickness is dx. The height is going to be the y value from the linear function minus the y value from the quadratic function. And the circumference is going to come from 2 pi times the radius. Now, what is the radius of one of these? Now, here my axis of rotation is actually in front of my x value. So I am going to kind of draw that here. My radius here is going to be 4 minus x. So that length is going to be 2 pi times 4 minus x. So my volume then is going to be an integral of 2 pi times 4 minus x times the y value from the linear function, which is 2x minus 1, minus the y value from the quadratic. So that's x squared minus 2x plus 2 times dx. The integral, in this case, we calculated this in the previous videos, the intersection points of those two curves is x equals 1 and x equals 3. It's believable from looking at the graph, but it is worth checking the algebra and making sure that that is true. So this is, I'm going to pull out the 2 pi, and we're integrating from 1 to 3. This would be 4 minus x times the quantity. Let's see, I have a minus x squared here. I have a plus 2x here and another plus 2x here, so that's plus 4x. And I have a minus 1 here and a minus 2 here, so that's minus 3 times dx. 2 pi times the integral from 1 to 3 of, I'm going to skip ahead a little bit on multiplying those two. So this is x cubed minus 8x squared plus 19x minus 12. That's how that multiplies. Antiderivatives, 2 pi times x cubed. Antiderivative is going to be 1/4 x to the 4th. Here we're going to have minus 8/3 x to the 3rd power plus 19/2 x squared minus 12x. All of this is evaluated from 1 to 3. I am going to evaluate each one of those pieces from 1 to 3. So 1/4. 3 to the 4th power is 81. Minus 1 to the 4th power is 1. Minus 8/3 times 3 to the 3rd power is 27. Minus 1 to the 3rd power is 1. Plus 19/2 times 3 squared is 9, minus 1 squared is 1, and then minus 12 times 3 minus 1. This is 2 pi times, this is 80 divided by 4 is 20, minus whatever 8 times 26 is divided by 3, plus 19/2 times 8. 8 divided by 2 is 4, so that's 19 times 4. And then minus 12 times 2, which is 24. Minus 24. So I'm going to skip ahead all of the fraction manipulation here. This ends up being 16 pi over 3. Which was in fact the volume that we calculated in the previous piece when we did it by slices. This was, I think, significantly easier. There was multiplying of polynomials and taking, using some power rules and dealing with some fractions, but it was a lot less complicated than doing it by slices.